we talked about the idea of a photon having both a wavelength, frequency, as well as possessing the properties of a particle. And so it has or possesses both wave-like and particle-like characteristics both at the same time. So what we want to talk about now is the idea that we can take this particle and we can calculate what those wave-like properties might be. So we're going to use or calculate what's called the de Broglie wavelength, which is the wavelength of a particle. It turns out all particles possess both of these different behaviors, although some of them are quite minuscule. We're going to look at an electron, and it turns out the electron has a wavelength and a frequency. It has those wave-like characteristics that we can actually use or we can take advantage of or we can observe. So the de Broglie wavelength formula is this. It is the wavelength is equal to Planck's constant divided by the mass in kilograms times v, which is the velocity in this case. Don't mistake it for the frequency. In this case, that v is velocity. So we're going to need to know all three of these things. And we're going to start with Planck's constant. So Planck's constant, 6.626 times 10 to the minus 34th joule seconds. It is a constant, and we have found that we've used it before, particularly whenever we have converted back and forth between wavelength and frequency of a photon or of light. We also need to know what the mass of our particle would be. In this case, we're looking at an electron. The mass of an electron can be found within the chapter that deals with subatomic particles. It's 9.11 times 10 to the minus 31st kilograms. I think your book, it might be in grams, but then you can convert it to kilograms. And lastly is the velocity. We said the idea is that this electron, whenever it's orbiting the nucleus or it's moving around that nucleus in what we're going to find, what we now may think of as like a solar system-like orbit. We're going to find later that's not really the case when we talk about orbitals and such. But it is moving at the speed of light as it moves around that nucleus. We know the speed of light is 3.00 times 10 to the 8th meters per second. Another constant for us to possess. So if you look at this equation, in reality, we have the mass which of our electron. We have this Planck's constant, which is a constant, and because of the particular particle, we know its velocity is the speed of light, which is a constant. Now we can just go ahead and plug everything into this equation, and we will be able to calculate what the wavelength of an electron would be. So, our wavelength is equal to Planck's constant times 10 to the minus 34th joule seconds, all over the mass, which is 9.11 times 10 to the minus 34th or 31st kilograms. We also know the velocity, which is 3 times 10 to the 8th. Meters per second. All you have to do the multiplication and division right in the calculator, and you end up with a wavelength of 2.42 times 10 to the minus 12 meters. And just for comparison, let's go ahead and convert that to nanometers. So we know that there are, in 1 meter, there are 10 to the 9th nanometers. So the meters will cross out, and we would be left with 2.42 times 10 to the minus 3 nanometers. And that would be the answer. I want to think about that number with you for just a second. When we're talking about visible light somewhere between 350 and 750 nanometers. That's the approximate range. That's about 1,000 times greater than the wavelength that we're seeing here for this electron. Now, that is quite small. However, the larger the particle gets, the smaller that wavelength will get. And if we compare this to the distant scale that we would observe the electron on, the size of the electron, it's not nearly as small as the wavelength would be for a baseball, for instance, which is much, much larger and has much, much more mass. So this is actually significant enough that we can observe things like diffraction of an electron. And we looked at diffraction of electron pattern through an aluminum foil in class, and we compared it to what that might be. That diffraction might be with X-rays. So we can actually observe this, although it's small. We can actually observe it for something like a bullet or something like a softball or a baseball. We wouldn't be able to observe that wavelength. So we've learned a little bit about what it means to have a wavelength and a frequency as a particle, and now we've talked about how we can calculate what that wavelength might be.